keep that, please. Okay, last time we discussed that S of 0 means the position of the object, plane, whatever, at time equals 0, correct? Yes. Nodding is helpful. Okay. We talked about how to find displacement using two different positions. Yes? Okay. We then made sure you understood that displacement could be both positive and negative. Okay. We talked about how distance traveled is different. Like displacement only depends on, where am I versus where am I now versus where am I going to be. That's displacement. And distance traveled depends on the path. It's all familiar. Okay. We then talked about how you could also calculate displacement by multiplying the velocity of the object by some amount of time. Also familiar? Okay. Did I introduce the integration symbol?
Yeah.
Good.
Well, that's where we were in the goal range. Yeah, that's what we were
Kind of about where we were.
That's for some.
Did we talk about how this is a large F?
Yes.
For some? Okay, good. Did we write that this, did we talk about how the integral is these, in this particular case, the integral is the velocity multiplied by some amount of time?
You wrote
Just
it in.
wrote it.
Just barely got that far. Okay, good. So, we talk about how integration then, you don't, like you need to keep reminding yourself that integration is a really, really simple mathematical process. All we do when we integrate is exactly what this symbol tells us. We're going to take velocity, and we're going to multiply velocity by some amount of time. Did we review what dt means?
No.
Yes? No? No. Okay. dt is not a new symbol. We've actually been using that concept since about October. What's that?
Wait, what was it?
I said dt is not a new symbol. We've been using the concept of dt since about October. So let's review quick. More commonly, we use the symbol dx. Okay? So no one talk. So hands up. What does the symbol dx represent? Okay, everybody, come on. What does the symbol dx represent? We've been using it since October. If you've forgotten what it means, it's okay. Just remember now. Kennedy.
Is it like it's a difference, but like a really small difference? Is that right?
Perfect, perfect. Yeah, dx is like, you have the right hand much. I knew you had the right answer. Look, think of a graph. Okay, you have an x-coordinate, and then you have another x-coordinate. And if you make those two x-coordinates really, really close, they're not the same x-coordinate. There's some difference between them. If the difference is infinitesimal, but still some difference, that's dx. How many knew it? 0.2 for Kennedy. So what's dt? Hands up. So same concept. What's dt? Garrett? It's a very small difference in time. So make sure when you see this, how many knew it? 0.2 forget. Look, make sure when you see dt, you see an amount of time. dt isn't like a time, dt is an amount of time. It's an infinitesimal amount, but it's an amount. Question?
So dx is that little space between two?
It's a small change in x, like it's some amount of distance on the x-axis. dt is some small amount of time. Okay, cool. So right here, when we integrate, we're supposed to take velocity and we're supposed to multiply by some small amount of time. Well, what happens is that mentally it's a little hard to wrap our head around an infinitesimal amount of time. So what I've done here is I've said, let's use numbers that are a little easier to comprehend. Let's say that for this airplane, for the first 5 minutes of its flight, the velocity of the plane is 7 miles per minute. Like for that entire first 5 minutes. Okay, the first 5 minutes, the velocity is 7 miles per minute. So if I know the plane has a velocity of 7 miles per minute, and I maintain that velocity for 5 minutes, then I know my plane's displacement, my plane's change in position, will be 35 miles during those 5 minutes. Okay, I'm always emphasizing how you must understand. If I were to make some sort of chart, like which concepts have a higher priority for understanding, we might talk about limits. Like it's important to understand what limits are, but they would be down the list a bit as far as priority for the AP test, as far as understanding. What I just said here, very high on the list. Like you have to talk with me until you are like, I know it and I will never forget it and I'll never misunderstand it. And when I take a velocity and I multiply by some amount of time, I am calculating how much the plane's position changes during that time. That must feel good to you. We want to talk about it.
So is that like an equation for velocity times time or something?
I'm not sure I want to make an equation out of it because that can cause trouble. But we do want to think of the idea. The idea is that if I know the velocity, and it really goes back to just paying attention to the words. This says the plane's position is changing by 7 miles every minute. So if I simply multiply by how many minutes go by, I'll know the total change in the position. Does that make sense? So the equation you're thinking of is true as long as some things like the velocity is always the same, but we won't really use that equation per se. But we do use the idea all the time. Like when 2 points for Sydney. When you look here, everybody, when you look here, I want you seeing this. We're just taking the velocity and we're just multiplying by some amount of time. Okay? Question?
And it tells you the distance it travels, right?
Oh, hold on. Don't say it that way, that will cause mistakes. It tells you the change in the plane's position. Now sometimes, Josh, the distance traveled is the same, but sometimes it isn't. So I don't want you to use that word, it'll cause mistakes. So this is calculating how much the plane's position changes. You can say displacement. It tells us how much, what the displacement of the plane is. There you go. Awesome. Okay. So remember, the equal sign doesn't mean this becomes this. The equal sign means these two things are the same. So what we have here is one method of calculating the displacement of the airplane. You can calculate the displacement of the airplane by knowing where was the plane and comparing that to where is the plane. That's what we did here. We calculated displacement by comparing position. We've now talked about how, like I said to Sydney and also Josh, that we can multiply velocity and some amount of time together, and we can calculate how much the plane's position changes during that time. In fact, Sydney's question about an equation, you could write this, and I don't think there's anything wrong with it. You could say the change in my position is going to equal, I still don't like it though, because we have to assume velocity is constant. And for our class, velocity is hardly ever a constant. So I think it's kind of a dangerous equation.
Did you say like final minus initial?
Yes, so the final position, subtract the initial position, will tell me the displacement of the plane. But this will also tell me the displacement of the plane, multiplying velocity times some amount of time. And if my velocity is changing, I can still use this. I just have to do a series of computations. That's the purpose of the big S.
Okay, so
Please.
this one.
Go ahead.
Sorry, this is like just when the velocity is all the same. Or does that? I guess. Well, it's just where it is. Like.
Oh, I think this is what you're asking. I want the whole room to answer this. So remember, equal doesn't mean this becomes this. Equal means these two things are the same. So this is one way to calculate displacement. This is another. So if we're using this method, I hope this is an easy question, but raise your hand and answer it, please. If we're using this method here, do we need to know anything about the velocity of the plane? Yes or no, why, why not? Hands up. Like if we're using this method to calculate the position, the displacement of the plane, do we need to know anything about the velocity of the plane using this method here? Lane is hopping. Go ahead.
I'm going to say no.
Tell me why.
Because I don't know. I don't look like it.
You're okay. You keep looking. You're doing just fine. 2 points. Charles.
No, because the displacement is change in position, and since we already have both of the positions.
Yeah, that's well said. One way to calculate displacement just means change in position. So if you know the two positions, you don't need to know anything about velocity. You just compare the two positions. How many knew it? 4. Okay. Did I say the name of this thing?
No.
This is known as the fundamental theorem of calculus. Elena's like, that sounds important. Yeah, I will refer to it as the FTC because I get tired of saying fundamental theorem of calculus. Sounds ominous, like you should play like ominous music when you say that. I've always thought it would be, I'll never find time, but I've always thought it would be fun to have like a little electronic box right here, and then just like a series of really cool sound effects. And just right at the right moment, press the button, the fundamental theorem of calculus, the lights flash, and lightning and thunder. And cool. As long as I can. Okay. As you are prioritizing, here's a little hint on priority. This is just to emphasize how important the few days we are discussing this right now are. The AP test has 108 points possible. Okay. I would say if you have a good, thorough understanding of limits, you probably can earn about 5 to 7 of those points. Okay? It's not bad. It's almost 10%. 108 points, right?
What if you so much was that? Is that a 1?
Well, that's just limits. Like we learned a lot more than limits. I'm just saying, I'm making a comparison. Look, you guys, whatever. Look, 108 points possible if you have a thorough understanding of limits. Probably can get about 5 to 7 of the 108. Then you're going to get more for other things, but that's limits, right? The fundamental theorem of calculus, if you have a thorough understanding of the fundamental, okay, I said that wrong. Without a thorough understanding of the fundamental theorem, like you got to know more, but if you don't have a good, thorough understanding of this, you are not going to earn, you're going to lose 30 points. Like there are that many questions that are going to involve this idea that if you don't have a really, really comfortable, oh yeah, Marin, stay comfy.
Inside joke.
Yes. That was you, right?
Yeah, that was me.
Good, good, good. Just as a word of explanation. So one day after school, the retake prep, right? Yeah.
No, just in like it was like the day before the test, just to do the.
Oh, they're just kind of just questions and things, right? I say that all the time, but I want you comfortable. Like it's not enough to do what I do. It's not enough to just memorize the formulas. You want to get to a place where you're like, no, I feel good. I'm comfortable. So Mary, when she left the room, was like, hey, everybody stay comfy. So I always say that I'm a shameless beggar for really cool signs for my wall. Like nice framed things. So I need Marin to make one, just have a little.
Oh, I will.
Like
I will.
Marin's message. She can just be like smiling, nice picture of Marin. Stay comfy. No, really, seriously, like I'm a beggar. I always want a nice sign. Okay. Focus. I'm talking to me, not you. Okay. Look. No, seriously though. What we're discussing right now, that's how high the priority is. If you're not comfortable with it, you're throwing away 30 out of 108 points. Like, it's that important. And it's not complicated. You just have to talk about it until you are comfortable. So one way to find the change in the plane's position is just knowing the positions. Everybody good with that?
Yeah.
The fundamental theorem is telling you that there's another way. You don't have to know anything about position. If you know the rate at which the position's changing, that's good enough. You don't need to know the position, just know the rate. We integrate that rate, we can find how much the position changes. That's the fundamental theorem.
If the velocity is positive, do we know that it's moving in the same direction the whole time?
So positive velocity always means the object is moving to the right. Negative velocity, object is moving to the left. 2 points for Carson. Anything else? Cool. Okay, so that's the fundamental theorem. Questions? Please.
So can you say like this is like position and this is just rate? Is that right?
No. 2 points though. This is change in position.
Okay, yeah.
And there's a little phrase that I like to use. It's not a rhyme, but it does have, in my opinion, kind of a rhythmic feel to it to make it easier to memorize. So memorize this. Look at what I'm pointing to as I say the phrase. If I integrate, that's what the big S means. If I integrate the rate at which position is changing. Okay, velocity is the rate at which position is changing. So if I integrate the rate at which position is changing, I will calculate how much the position changed. Because that's what displacement is. So if I integrate the rate at which position is changing, I will calculate how much the position changed. That's how I memorize the fundamental theorem, with that little saying. That's how I memorize this formula. I don't memorize the formula as a formula, I memorize it as a concept. If I integrate the rate at which position is changing, I get how much the position changed. Integrate, like look at these numbers, it helps. This is saying that for 5 minutes, the rate at which the position is changing is going to be 7 miles every minute. Well, integration is just multiplying and adding. So when I multiply those together, I get how much the position changed for that time period.
Can you say it one more time?
And it has a little bit of a rhyme at the beginning to help get you going on this little melodic statement. Got my special effects button and play some music. If you integrate the rate at which position is changing, if I integrate the rate at which position is changing, I calculate how much the position changed. Question, please.
So I know this one we're not subtracting the final. We're not subtracting the final position from the final minus initial. Never mind.
You're good?
Yeah.
2 points. Anybody else? Good. Awesome. Okay. So let's go to the buff packet now. We haven't really used it. You need one, right?
Yeah.
Say that in a more polite way. It sounds terrible. You need one. Lauren, would you like a packet?
Thank you.
More polite. Sorry about that. As soon as I said that, I'm like, that sounds rude. Also accusatory. Okay, buff packet. So we did nothing in the buff packet last time, correct? Okay, the first part goes pretty fast. Raise your hand if you know the answer to A. The question was just asked a minute ago. Raise your hand if you know the answer to 1A. Raise your hand if you know the answer to 1A. I just want to work on this together. Raise your hand if you know the answer to question 1A. Let's go, Mary.
7 to 10 and 27 to 40.
Tell me why you said that.
Because it's a velocity graph. decreasing from 7 to 10 and increasing from 27 to 40.
So you're looking from time, like this time.
Oh, sorry, I was looking at the wrong thing. Sorry, 0 to 10 and 27 to 40.
Okay, 2 points for Marin. The mistake you're making is you are identifying when the velocity, roughly, you are identifying when the velocity is increasing, but that's not when the plane is moving to the right. No worries, 2 points. Who knows how to tell when the plane is moving to the right? Dawson?
Is it the whole time because the velocity is always positive?
Right. So whenever the velocity is positive, part of the plane is moving to the right. And in this example, the velocity is always positive, so the plane is always moving to the right. How many do it? 0.2 for Dawson. So write something in your packet to remind you of the concept. Don't answer the question. Like, write down whatever you need to write so you know you won't forget the concept. As always, just having an answer isn't really much use. So. Okay, let's talk together. Raise your hand when you have an answer for B. Go. It says to use the graph, so don't look at the table, look at the graph.
Sorry, no. Sorry, like 11. Yeah, I'm just looking at that. The table's a little bit ambiguous. Yeah, whatever. Same completely.
Who has an answer? Show me your hand. Who has an answer? Show me your hand. Let's go, Kylie.
Mr. Smith,
Yes?
Christian Hill is being checked out.
Oh wait, too bad for him.
Thanks.
Couldn't resist, Christian. Who knows this one? Hands, come on. What is it, Kylie?
Is it never because the velocity is never 0?
Oh, 2 points. Good comment. Misunderstanding. No big deal. So positive velocity means the plane's moving to the right. Negative velocity would mean plane's moving to the left. As I look at these velocities, you're going to see it. I'm just going to help you, okay? Right here, what's the velocity? 7. And just kind of look at the graph. About here, what's the velocity? About here, the velocity is?
9.
Okay, so if the velocity is getting higher and higher, the plane is speeding up. Because the velocity is the rate at which the position changes. So this is saying, hey, the plane's position is changing by 7 miles every minute. But then, no homework tonight, by the way. Josh and Lori are celebrating wildly. Look up. Come back. I'm not sure it's that significant, but whatever. Did you see your mistake? Not really. Talk to me.
Because I get that it's like decreasing, but it's not this, I don't know. I guess it's
Yeah, what's happening, so what's happening here is because the velocity is getting less and less, the plane's position is changing by an amount that is less and less to the right. Like I'll do my best to walk it. Like if I'm going like this, my position is changing by like 3 feet every second. But if I start going like this, I'm still going to the right, but now my position is only changing by 2 feet every second. Now if I go like this, I'm still going to the right, my position is only changing by 1 foot every second. So I keep moving to the right, but I am slowing down.
So if it's slowing down, where the slope is 0, or just when it's decreasing?
So we would say that at about time 7.5 roughly, that's the moment when the plane stops going faster and faster and starts to go slower and slower. The plane continues to slow until about time 27.5. So that's the time period over which the plane is slowing. Does it feel good?
Yeah.
Please.
So, like at the first thought at t equals 5, would it still be going faster even though the slope is less? Like the slope is decreasing?
Good question. Everybody listen to this one. Listen close. Keep for Ashley. Okay. What's happening is, okay, everybody, as long as the velocity is getting greater and greater, so to answer, so what you're doing is really smart. You have to, in this class, kind of change how you look at things all the time. For this question, we are only looking at the dots. We don't look at the slopes at all. Because as long as the dots are going up, the velocity is getting greater and greater, which means the plane is going faster and faster. Now, if we look at the slopes, what we see is the rate at which that velocity changes. This is hard to say, but it's like the plane is going faster and faster, but it's at a slower and slower rate.
Okay.
Is that kind of what you meant?
Yeah.
Yeah. Other questions?
Going faster and faster.
If you think of a car, it's a lot easier. If you think of a car, it's a lot easier. If you get in your car and go to a test track, so it's all safe. Okay, most cars will accelerate, like they'll speed up very quickly in the beginning. Like if you really step on the gas, right? It'll speed up very quickly in the beginning, but eventually we'll keep speeding up, but not as much. That's what Ashley's talking about. Does that make sense? The car's still speeding up,
It's still getting faster, but just not.
but it's not getting faster and faster as fast.
Yeah.
It's hard to say. Please.
Is it possible that like if you have position graph and then you have to find like the velocity stuff in there? Or would they just do the other displacement without the
Oh, gotcha. Okay, quiet. If they're asking whether the particle is speeding up or slowing down, one way they can ask that is by showing you this graph of velocity. So you need to keep track of that. For now, that's enough for now. We don't. If we mix in something else, it gets too confusing for now. So is that okay? Okay, 2 points. Anybody else? Okay. Look, we already talked about this one, right? S of 0 is the location of the plane. Okay, so you know that one. Moving on. We already talked about S of 40. Nod if you know what S of 40 means. Okay, so you know how to fill out that. We've already done this one. That was our discussion earlier. We've already talked about change in position, so nothing new here. So I'll give you a second to look at it. Give you a second to look at it. Talk to me if any of this is not still making sense. So just do D, E, and F quick. Ask me about anything, Gary.
So back to 1B.
Which one?
B.
B.
If we don't have the graph, I mean, will it ever ask for us to look down the velocity graph? I just gave the table.
It's kind of related to what Elena asked. There will be 2 points for Garrett. There will be questions that talk about whether an object is slowing down or not, and those questions may not involve a graph at all. If all they do is give you, well, we better leave it alone. Like, I think it's going to get too complex for now. But so we'll just have to address it later. Questions?
How would you, for that one, how would you format like how you answer the question? Would it just be like t equals 0 to t equals 40 or
Yeah, that's fine. Like you could just write this. You could say t equals 7.5 to t equals 27.5. Because you get tested on units in this Unit 4 test, I would make sure I threw in the units.
Okay.
You okay for now, Garrett? Anything else? Charles is tired.
What's up?
Everybody good? Okay. So any questions here? Sorry, any questions here? Moving on. Okay, answer 2A, please. Raise your hand when you have it. Go. Answer 2A, raise your hand when you have it. Actually do 2A, B, and C. The smiley face and frowny face is because I somehow thought I was being clever, and they're kind of stupid questions, but I thought it was funny at the time. No, I'm not sure it's very funny, but whatever. So answer those three. Show me your hands when you have the answer to all three. Feel free to talk to each other. No, so the fact that the velocity is positive, so these, it goes back to what they mean. Velocity is raised at which position changes. So this is saying your position is going to change 7 miles every minute. So are you moving? So if your position is changing by 7 miles every minute, are you moving to the right or to the left? Good. Now we want to know whether we're speeding up or slowing down. We want to know, well, look right here. At time 0, you're moving to the right 7 miles every minute. But at time 2.5 minutes, you're now moving to the right about 8 miles every minute. So did you speed up during that time, or did you slow down? You sped up. So your velocity became greater. Then the next 2.5 minutes, now your velocity is about 9-ish. Did you speed up or slow down? Yeah, that's the dumb joke. I'll talk about it. Hold on. Who has an answer to A? Show me your hand.
We're not looking at this.
Hands. Who has an answer to A? Who has an answer for A? Hands. Come on. Who has an answer for A? Carrie.
T equals 0 to T equals 7.5.
And the units would be minutes. Is there another answer?
T equals 27.5 to T equals 40.
Raise your hand if you have that written on your paper. Point 2 for Carrie. Question? So, yeah, please.
We could write that in parentheses as an interval as well, right?
Uh-huh. Like that?
Mm-hmm.
Uh-huh. 2 for they'll take either one in this case, because there is a dispute in the mathematical world as to how to interpret whether we should say it starts right at 0, so they're not super critical of that one. I guess technically we probably should have done a bracket here, because right away the plane is speeding up, like right away. Whether we put a bracket or parenthesis here, that's the mathematical dispute. They don't seem to be too critical on the AP test, so I think you're fine either way. So, Mary?
It was like greater than 0 is less than t, and t is less than 7.5.
Also fine. Yeah, they'll accept that. 2 points.
Would you start with the units on
They don't ever require the units unless they actually have the word include units. I've never seen them take away points unless they prompt you for it. So Yeah, if they prompt you for it, you'd want to put minutes here. For sure. Point? No? Okay, so here's the question that I somehow thought was humorous. It's kind of dark humor. Someone else at the door? I don't know. See, if I keep doing this, he keeps moving away from the window. So, if you have an airplane that's not a, vertical takeoff, right, like a hover capable, which some planes are nowadays, the plane can never be at rest. Yeah.
It wouldn't be at rest, it'd just be falling.
Yes. Yeah, planes cannot be at rest. It doesn't work.
Wait, so would it be a zero? A T of zero? Or
Uh,
a T of zero?
The idea here was that they kind of captured this as the plane's already moving. It's kind of a dumb. These are dumb. Just cross these off, please.
Wait, what happened to the airplane with the rest?
Says the velocity equals
If
zero.
the plane is at rest, the velocity will be 0, and where will the plane be?
But won't it be going?
On the ground.
So it just slammed into a mountain, basically.
Or it fell out of the sky.
But then isn't it increasing downwards?
No, I didn't say it. It's not when it's falling. It's after it has fallen.
Okay.
Like, no, see, finally got it away. No, look, Chris is right. As the plane is falling, it does have a velocity that's directed downward. Once
So
the
is that
plane
negative
hits
velocity?
the ground, now it has no
Now it's
velocity.
at rest.
Now it is at rest.
Yeah, how do you show a velocity that's directed downward? Crap.
Just cross these off. Okay, moving on. Should not have asked those. It was a weak moment. Okay, as I said, I don't want you doing the homework yet tonight because the concept we were discussing literally are required for about 30 of the 108 points. I want to talk about them until, as Marion said, you are comfortable. Okay. So I don't want you doing homework yet. Okay, we talked here about, like we kind of tried to get a sense of what it means to integrate. I want you to switch to your notebook now, so not the buff packet. Just switch back to your notes. And I want to discuss in a little more detail what it means to integrate. It's crucial that this makes sense, okay? It's another huge topic. And the good news is it's really not hard to understand. You just have to talk about it enough that you feel comfortable. Okay? So we're trying to do that mathematical computation, so write that down in your notes. Okay, so when you see an integral, you're not supposed to see like what you're supposed to see is something really simple. This says, start at time equals 0, go to time equal 40. And during that time period, take every single velocity that is in that time period and multiply every velocity by some amount of time. So you do the multiplication over and over again. And then the big S says you're supposed to add them up. Okay? That's what integration is. So we're actually going to start doing the integration. So we're going to say this is, now we're going to say approximate, because it's really hard to talk about an infinitesimal amount of time. So we're not going to talk about an infinitesimal amount, but if you understand what's happening with a real amount of time, like a finite amount of time, it's not really too hard to kind of extend it to an infinitesimal amount. So I need to start at time 0. So oh, wait a minute, hands up. What does V of t mean? What's V of t mean? Hands. What does V of t mean? And this is where precision is important. I keep reminding everyone. When you are not precise, you lose points. Like, what does V of t stand for, Laura?
The velocity.
At any time.
At any time.
So make sure when you see this, you're thinking, hey, that's the velocity at any time. The velocity at any time. How many knew it? 0.2 for Laura. I'm starting at time 0, so that's the velocity I want to start with. So what you should write on your paper is v of 0. The velocity at time 0. This symbol tells me what to do next. It says to multiply that velocity by some small amount of time. Ideally an infinitesimal amount of time, but hard to think about that, so I won't. Instead, I'm going to use something simple, 5 minutes, because that's easy to see on the graph. I'm going to multiply this by 5 minutes. Question? Okay, the integral says I'm supposed to do this for 40 minutes. I've only done it for a 5-minute time period, so now I keep going. So I say plus, that's what the S is for, a sum. And I go to, so what I did there is I said, okay, I'm supposed to take every velocity in the 40-minute time period, but taking all of them is too many. So what I did instead was I looked at the first 5 minutes and I said, well, let's just say that the velocity is 7 for the first 5 minutes. So instead of the purple graph, let's say we actually have the brown graph. Just because it's hard to take every velocity. So now what I'm going to do is say, well, for the next 5 minutes, the velocity is different. Now the velocity is going to be way up here, 9.2. So for the next 5 minutes, I'm going to have the velocity be 9.2. So I'm using the velocity at time 5. So I take the velocity at time 5, and I multiply that by 5 minutes. So I'm doing what the integral says. I'm taking a velocity multiplied by some amount of time. I want to talk about it a bit. Cool. Now I keep going. So raise your hand if you know what I should write here, following the same pattern. Show your hands. Feel free to talk to each other. What gets written next following the same pattern? So hands up. Come on. What's next following the same pattern? Sophie? Perfect. I simply go to the next 5-minute time period, and I'm going to take the velocity right there. So it went up just a little bit. I'm going to use that velocity for the next 10 minutes. So that's this. How many knew it before she said it? Point to for Sophie. You want to talk about it, please. Yeah, you're good. Anybody else? Cool. Plus, hands up. What's the next one? What's the next one? Sarah? How many knew it? 0.2%. Anyone have a question? Please.
Are we just breaking it into like chunks of like 5 minutes because like that's what the table did?
Yeah, just kind of following the table. So we could have done it a different way. That was just convenient.
Okay.
Kind of like this. 2 point.
Instead of 5 minutes, could you do like 10 minutes or 20 minutes?
Or 1 minute. Yeah, I'd have to read the graph if I did it by 1 minute. 2 point.
What about when it says for some intervals of equal length and values?
So that's why I had you put this in your notebook.
Okay.
No worries, 2 points for Abby. So we're not actually answering this question. That's why you're in your notebook, right? Everybody's in their notebook? Okay, good. Any questions here?
You're welcome.
Okay, look, it gets kind of boring at this point, so you just go like this. Okay? Way too tedious to keep writing it, so just keep following that pattern. Okay, look over here. Look, what we did is we essentially changed the graph of the velocity. The actual graph of velocity is the purple. And if I were doing this integral perfectly, I would need to do this exact pattern with each and every velocity. So my dt would be very, very short. Understand? Now, it's an infinite number of terms, so no, I can't do it. Okay? So that's why I didn't try. Are you with me? This, what I've written here, this approximation, it's as if the graph of velocity has changed. And the graph is what I drew here. Okay? It's like and you can see that the graph I'm drawing isn't exactly the graph of velocity, but it does roughly follow. Okay? Question? Awesome. Question for the whole room. This is the integral we're trying to compute. We know that we cannot compute it precisely because that would mean we'd have to have an infinite number of these terms being added up. Are you with me? It is important that all of you understand, though, you have control over how accurate your approximation of the integral is. So who knows how to control the accuracy of the approximation? Hands up. This is where I'm testing to see if you understand it. How do you talk to each other? How do you control the accuracy of the approximation?
We don't know the velocity in it.
Hands up. How do we control the accuracy of the approximation? Calvin?
By like the time interval. That makes sense.
It is absolutely true that we control the, I'm going to have you say a little bit more. We control the accuracy of the approximation by the time interval. So give some details to how we use the time interval to control the accuracy.
So if we, in this case, we're taking it every 5 minutes, if we took it every minute, it'd be more precise.
Perfect. How many knew it? 2 points, 3 for Calvin. Good. Okay, look at me, look at me. Raise your hand if you are comfortable with that. Like, show me your hands. Who's comfortable with that? 2 points. Look, it's easy, right? Like, once you see it, it's not a hard concept. It's easy to remember. Shouldn't have trouble ever remembering it. Okay? Very good. Awesome. Okay. Now go back to your buff packet. Back to your buff packet. Okay. On a test, the test writers, whenever they ask someone to approximate something, they have to control the question because it gets too hard to grade. If you ask someone to approximate and like students come up with 16 different ways to approximate, nightmare for grading. So the way they control that is they ask you to do a specific type of approximation. So we're doing the buff packet now. The type of approximation they're asking you to perform is what's known as a left Riemann sum with 4 subintervals of equal length. Okay? If our previous discussion made sense to you, it should be really easy for you to do this. For example, when they say do this integral from 0 to 40 with 4 subintervals of equal length, raise your hand if you feel like you know what that means. We're supposed to perform the integral with 4 subintervals of equal length. What does it mean, Lizzie?
It just means you'll divide the graph into 4 equal amounts of time.
Perfectly said. Learn to talk precisely. It's perfect. Divide the graph into 4 equal segments of time. How many knew it? 0.2 for Lizzie. Okay, warning. I have seen students come to my desk during tests, and here's what they've done. Watch the error. They have a problem like this on the test. They read 4 subintervals of equal length, and they do this. And then they come to my desk and they say, the problem's broken. Like I can't get 4 subintervals. Okay? So don't ever divide a table like that. Do this instead. This seems kind of trivial, but it really makes a big difference. we need to go from 0 to 10. Then from 10 to 20, 20 to 30, 30 to 40. That's how you divide. Question? Cool. Okay, so just like I talked before, we want to perform this integral. So, on many AP questions, if you do not write the integral, they will take away a point. So we're practicing for the written section. Make sure whenever you do an integral, you write down the integral. It is an approximation. If you forget to put an equal sign, I don't think I've ever seen them take away a point for that. But it is an approximation. We need to do what we talked about. We're supposed to go to the first time interval, okay? And for that time interval, we're supposed to pick a velocity. Well, there's technically an infinite number of different velocities within that interval. We can only pick one. The word left tells us which velocity to pick. So raise your hand if you think you know which velocity I should be picking. The word left tells you. You look at the subinterval, you're supposed to pick a velocity for that subinterval. Rachel?
Would it be 0?
Perfect. So because 0 is the time that is on the left of the subinterval, that's the time I pick. So I'm going to write down here a v of 0. How many knew it? 0.2 for Rachel. Question? Cool. Okay. Now I need to multiply by dt. dt is some duration in time, ideally infinitesimal, but not for our approximation. Just say it out loud, please. What's dt for our approximation? 10. So I multiply by 10. Question. Now remember the fundamental theorem here. The velocity is 7 miles per minute. I'm multiplying that velocity by 10 minutes of time, which means I'm getting a value of 70. Say the units out loud. What are the units? Say it. Louder? Louder?
Miles.
There we go. So hands up, what is this computing? 1 second, Justin. What's this computing? Hands, what is this finding? When we integrate this, what are we finding? What are we finding? So Sydney?
It traveled 70 miles in the distance between 0 and 10.
Good. I want you to change the wording just a little to prevent mistakes. Best to say that the position of the plane changed by 70 miles during those 10 minutes. How many knew it? 0.2 precision. That's the fundamental theorem. We've talked about that before. It's right here. When we're integrating velocity, it's the little rhythmic statement. When I integrate the rate at which position changes, I find out how much the position changed. That's what happened here. Question? Then you just say plus. Hands up, what goes here? Let's go, Sarah.
Velocity at time and times 10.
And this line would end up being 9.5 multiplied by 10. How many knew it? 0.2 for Sarah. Anyone want to talk about Justin?
Okay, so we have a table that's telling us that like 5, 10, right, whatever, and that's the times we're using, but will they ever not give us the table and we have to figure out, like, at the start of the time what the native velocity is? Like on the last question, you were like drawing the horizontal line saying like at 0 it was 7. Will we ever do that without a table?
There have been AP questions similar to this that did not use a table. There have been questions that used a formula instead. And so what I did is I just used the formula to create the table.
Okay.
Yeah. I've seen questions like this that used a graph instead of a table, but the graph was labeled in such a way that I could just get the information from the graph. And as Justin said, part E right here, part E, what we're doing is we're saying instead of the velocity doing this, we're saying the velocity is going to be 7 for the first 10 minutes. So we're saying the graph would look like that. And then for the next 10 minutes, we're saying the graph would look like this. Like so. Question? That's what this is talking about. What goes here, quick? Mary?
We have 20 times 10.
2 for Marin. What goes here? Goes here. Let's go Aisley.
We have 30 times
2 points for Aisley. What goes here? What goes here? Let's go Josh.
We have 40.
Oh, hold on. Speak to your weight. Go, Abby.
Oh wait, since it says 4 subintervals of equal length and we're only going to 40, would we stop at V is 30 times 10?
Yeah.
Good work. Did it on purpose so you'd see the mistake. Yeah, look, it's exactly what Abby said. We're trying to do the integral from time 0 to time 40. We have 4 equal subintervals. This subinterval, like this computation takes care of the first 10 minutes. This computation takes care of the second 10 minutes, third and fourth, so you don't want this. Please.
So it's kind of like whatever velocities, you just like kind of add that time to it, like because it's like covers like the first 10 minutes and you have 10 minutes of time, so it's like.
Right. Yes, that's the right idea. Very good. 2 points. Anybody else? Cool. So fixing this a little bit. So the last one I did a little dot, dot, dot thing. Don't ever do that on the AP test. That was just for your notes, okay? On the AP test, you have to show the 4 subintervals. Questions? Cool. Okay. Something else you need to be able to see here. Please, Sarah.
With your equal signs, would you do the approximation or would you continue the equal? Because you have like D2 equals, or approximately, so then below is equals.
1 second, I know exactly what you're talking about. So technically you need to have approximation here because dt is not infinitesimal. It's kind of a weird math thing, but it's technically an equal sign here because all of this does equal this exactly. But I've not seen them be picky about it, so I'm not going to stress too much. But is that your question? Good work. Anybody else? Make sure. The problem says you have to show the computations that lead to your answer. So you do have to show either this in green, or you could show this line here in green, as long as I finish the computations, like I say, okay, now 4.5 times 10 plus, let's see, 2.4 times 10. So you can show, you have to show the integral. Then you can show these 4 or these 4. You don't have to show both, just one or the other. So, question? You can't just do this. You can't just show this computation. Like in, say, 70 plus 95 plus 45 plus 24. They want to see that you're understanding what integration is. So, questions? Cool. Okay, look here. Any questions about what I did on E? Like, this is what this really is representing. It's as though the graph of velocity changed and looks like what I drew. Okay, we're almost done, and this should be telling us about the assembly soon. Okay, another connection you have to be able to make is when you look at this graph and you look at the computation, this little multiplication here can be represented geometrically on this picture. Geometrically means you can draw a shape that represents this, the 70. Talk to each other and raise your hand and tell me, how can I draw some sort of shape that matches this computation of this times this is 70? Like there's something you can look at visually and go, oh, I see it. This times this being 70, I can see it right there. Ideas? Old blank book. Justin?
Would you like turn it into like a rectangle so you can take the area of it?
So what Justin is noticing is the 7 is not just this number. 7 is also this length. 7 is just, this is really a critical connection. Look, 7 is just that length. 10 is not really this number. 10 is really this length here. So 7 times 10 7 times 10 is this area. Question? Do you see it? Okay, stay with me, don't check out. Okay, raise your hand if you remember. How do we control the accuracy of the approximation for our integral? Hands up, come on. How do you control the accuracy of the approximation? Charles?
Like changing the time interval.
So I change the size of dt. So if I want the integral to be more accurate, Charles, do we make dt bigger or shorter? Short. Look at the board. Look at me. If you make dt shorter, what happens to the little rectangles that you are computing? They get narrower, right? Now make sure you can visualize this. If I make the rectangles more and more narrow, they're going to fill the space under the velocity curve more and more precisely. Like the narrower the rectangle, the better they fill the space. Understand? That's why a lot of people will tell you integration means area. Okay, I don't want you to memorize that. Integration doesn't mean area, but in some cases, when we do an integral, it's not all cases, but in some cases when we do an integral, we are definitely computing an area. And if we could make dt infinitesimally narrow, we would compute this area under the velocity, like between the velocity curve and the axis, perfectly. Questions? Cool. We should be doing something rather soon, but you know, sometimes how it goes. We'll pause right there for today. No homework, please. What you want to say, please.